Hi, my name is Travis Cawthon, and today I will be presenting a microhydro site assessment that will determine the feasibility of a microhydro system on the site proposed by a client. The client has presented the following information about their proposed site. The site consists of an 8-acre residential property that is located 200 feet away from a stream. Given this information, this is what we know regarding the feasibility of the site. We know that the stream is in close proximity to the residency, which is preferred so that transmission loss can be minimized and the system can be made more efficient. At first look, the stream has adequate enough flow to viably direct part of the stream to power a turbine. Since this is a residential property, there should be enough incentives provided by the government to make the cost of this project viable. After taking measurements for the flow and head of the stream, the following numbers were calculated. Maximum flow was found to be 3,590.65 GPM. Minimum flow was found to be 237.88 GPM. The stream was found to provide 65 feet of head. In any microhydro system, flow and head will determine the output of the overall system. Luckily, the two characteristics correlate in a way that compensation can be made if one characteristic is lacking. Meaning, for example, if the amount of head your stream supplies is too low, a greater amount of flow can be diverted from the stream to compensate for the missing head. The design flow will be based around the minimum flow to account for high and low flow periods throughout the day. By using minimum flow, this will guarantee that the system will maintain a constant flow on an average day. However, we cannot use the entirety of the minimum flow, as the impact the system will have on the surrounding environment must be minimalized. Therefore, the design flow will be 150 GPM to leave adequate flow left in the stream to maintain the balance of its ecosystem. Moving on to the system design, the microhydro system will consist of the following: a penstock, intake system, turbine, and balance of system. I will discuss each of the components in detail. The penstock shall consist of 4-inch high-density polyethylene pipe. This material is desired for its durable characteristics as it is also flexible, making it easier to follow the contours of the land as a path is made from the stream to the powerhouse. This material can be exposed to the elements and protects against freezing in the winter, as opposed to PVC pipe that must be buried yet still has a chance of freezing. Each section of the pipe will be sealed using fusion welding, ensuring that the material does not leak or deteriorate once in use. The intake system will consist of an open-ended pipe with a settling container. This is a relatively safe and cheap intake system to use, as maintenance is relatively low. The intake system consists of a 55-gallon barrel that will serve as the settling container and a 1/4-inch wire mesh that will serve as a screen for any debris that enters the intake. An additional smaller mesh screen is optional if the client wishes to screen out even finer debris from the system. Any sediment that happens to enter the intake will settle to the bottom of the container, ensuring that the system will not be damaged from sediment intake. The only drawback to this type of intake system is the splashing that can occur inside the container before water enters the penstock. Splashing can cause air bubbles to form within the penstock, disrupting the constant flow of water and making the nozzles at the turbine sputter, which will in turn damage the turbine. In any case, using a 55-gallon barrel as opposed to a tub or trough has been known to fix this problem. Overall, this intake is a great option for a first-time microhydro installation. However, I recommend that if this intake starts to deteriorate, an investment be made into a more durable intake, such as a self-cleaning stainless steel spillway with a Kawanda effect screen. The turbine will consist of a turbo impulse turbine to account for the high amount of head given by our system. The system works by ejecting water at high pressure from the turbine nozzles at the turbine itself, allowing it to spin and produce electricity. The turbine will feature two sets of nozzles, two 5/16" nozzles and two 5/8" nozzles. Using two different sets of nozzles will allow the system to have varying modes of capacity. For instance, in times when flow is low, The two 5/8 inch nozzles will be used, and in times of high flow, all 4 nozzles can be opened for maximum power production. This will allow the system to be prepared for the variations in flow year-round. The balance of system consists of 3 components: a charge controller, battery bank, and an inverter. When designing a battery bank for a microhydro system, we want to allow for approximately 1 day's worth of storage in case of low output by the system. This system's battery bank will consist of 28 12-volt 220 amp-hour batteries in parallel, allowing for a total of 74 kilowatt-hours of storage in total. The output of the system will vary depending on the amount of nozzles open on a given day. The two 5/16 inch nozzles produce 93 watts when open. The two 5/8 inch nozzles produce 740 watts when open. When all 4 nozzles are open, an output of 833 watts per hour can be expected. On an average day, we can expect this system to offset the client's power usage by about 13.7 kilowatt hours. The costs for the varying components were researched and found to be as follows. High-density polyethylene piping, $293 per foot, approximately $586 total. Our intake system was found to be around $40 to $300. The turbine was found to be around $1,995. The battery bank cost approximately $4,200. The charge controller cost $600. The inverter cost $230. The total cost of our system was found to be around $7,651 to $7,911. There are incentives offered by the government to offset the cost of the microhydro system. The first incentive we will look at is a financing program that provides a loan at 8% that will be paid back at any time over a period of 20 years. All the profits made by this program are recycled back into the program itself, so the main goal of this program is just to help push the development of renewables. The second incentive we will look at is offered by the Tennessee Valley Authority. This incentive offers $1,000 upon installation and will buy all electricity the system produces for a 20-year period at varying rates. For the first 10 years, the Tennessee Valley Authority will purchase it at retail rate plus 2 cents per kilowatt hour. For the second 10 years, they will purchase it only at retail rate. Note that the second incentive will require the client to connect their system to the grid via a power meter. Assuming the client will want the system to be connected to the grid, they will need to contact their county government to receive the permits necessary for installations. Exemptions should also be obtained from FERC or the U.S. Army Corps of Engineers. Lastly, the client should make sure they have obtained all water rights necessary to legalize the amount of water they are diverting from the stream for this system project. Thank you. That was the assessment I made for this particular microhydro site proposal. I hope you enjoyed.